Did the James Webb Space Telescope just find our cosmic ancestors? Telescopes do not uncover family trees. They collect light, cold, distant, ancient light. And yet when you follow that light far enough back in time, it begins to tell a story that looks remarkably like ancestry. Because every atom in your body has a history. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of your cells. None of these ingredients were present when the universe began. In the first moments after the Big Bang, reality was astonishingly simple. Almost everything that existed was hydrogen. A smaller fraction was helium, and that was essentially it. No carbon, no oxygen, no silicon, no iron. Yet here we are living on a rocky planet orbiting a metal-rich star inside a universe that somehow learned how to build complexity from near nothing. That immediately forces a question that is not philosophical but physical. Where did all of this come from? For decades, astronomy has given us a clear answer. The heavy elements that make planets' chemistry and biology possible were forged inside stars. Not all at once and not everywhere, but gradually. Generation by generation, star by star, death by death. In that sense, we're not just made of stardust. We are made of ancient stardust, material that has passed through stellar interiors, survived titanic explosions, and wandered the cosmos long enough to become part of a solar system that formed very late in cosmic history. And that timing matters. Our sun is about 5 billion years old. The universe itself is roughly 13 to 14 billion years old, which means that for more than half of cosmic history there was no Earth, no sun, and no planetary system like ours. The universe was already old before we arrived, so if stars are responsible for enriching the cosmos, logic demands that there must have been earlier stars, stars that lived and died long before our galaxy took its present shape. Stars that began the process of turning a chemically simple universe into one capable of producing structure planets and eventually observers. But here is the problem. Until very recently, those first stars existed only in theory. We built models, we wrote equations, we ran simulations, we understood what should have happened if gravity, nuclear physics, and cosmic expansion behaved the way we believe they do. And all of those models pointed toward a missing chapter in the universe's story, a generation of stars so ancient, so massive, and so short-lived that none of them should still exist today. If that is true, then finding them directly would be extraordinarily difficult, not because they were unimportant, but because they vanished almost as soon as they appeared, leaving behind no survivors, only consequences, which raises a subtle but profound question. If the first stars are gone, how could we ever know they were real? The answer is the same way we reconstruct most of cosmic history, not by finding the actors themselves, but by studying the light they left behind. Light that began its journey when the universe was young. Light that has been stretched, diluted, and reshaped by billions of years of cosmic expansion. Light that arrives today carrying information about conditions that no longer exist. This is where the James Webb Space Telescope enters the story, not as a magical eye that suddenly sees the impossible, but as a carefully engineered instrument designed to test ideas we have carried for decades. Because if Webb has truly detected evidence of the first generation of stars, then this is not just a discovery about distant galaxies. It is a discovery about ancestry, about the earliest step in a chain of events that eventually led to us. To understand what Webb may have found, we have to go back further than galaxies, further than planets, further even than familiar stars. We have to return to a universe that had almost nothing in it at all. To understand why the first stars mattered so much, we have to strip the universe down to its earliest state. Not poetically, physically. In the aftermath of the Big Bang, the universe was hot, dense, and expanding rapidly. For a brief window of time, conditions were extreme enough to assemble atomic nuclei. Protons and neutrons collided, fused, and froze into the simplest elements nature allows. Hydrogen formed first. Helium followed shortly after. A trace amount of lithium appeared as well. And then the process stopped. The universe cooled too quickly. Expansion pulled matter apart faster than nuclear reactions could continue. There was no pathway to carbon, no route to oxygen, no mechanism to build anything heavier in meaningful quantities. This was not a failure of physics. It was an inevitability of it. The Big Bang was never a factory for complexity. It was a starting gun. For hundreds of millions of years after that initial moment, the universe remained chemically primitive. Vast clouds of hydrogen and helium drifted through expanding space. Gravity slowly gathered them into denser regions, but chemically speaking, the universe was still almost empty. And this chemical simplicity had consequences. Without heavy elements, there were no solid surfaces, no dust grains, no efficient ways for gas to cool and fragment. The familiar structures we associate with galaxies today had not yet emerged. Even light behaved differently, moving through a universe that had not fully settled into transparency. This era is sometimes described as the cosmic dark ages, not because nothing existed, but because nothing was shining yet. No stars, no galaxies, no sources of sustained light. Just gravity quietly at work amplifying tiny irregularities left over from the Big Bang. Regions where matter was slightly denser than average began pulling in more material. Over time, those regions grew, slowly, relentlessly, and eventually something crossed a threshold. As hydrogen gas accumulated, pressure and temperature rose. In the densest pockets, gravity won. Matter collapsed inward. Temperatures climbed high enough for nuclear reactions to ignite. The first stars were born, but these were not stars like the ones we see today. They formed in a universe with no metals, no elements heavier than helium to help regulate the process, no efficient cooling agents to limit their growth. The physics of star formation was operating under entirely different conditions, and that difference matters, because when stars form today, heavy elements act like control systems. They radiate energy away, they slow collapse, they help fragment clouds into many smaller stars rather than a few enormous ones. Remove those elements and the rules change. Gas collapses faster. It stays hotter. It resists breaking apart. And instead of producing a wide range of stellar masses, the process becomes biased toward giants. This is the environment in which the universe's first stars took shape. Not in a chemically rich cosmos filled with debris from earlier generations, but in a universe that had never experienced stellar death. A universe that had never been enriched. A universe that had not yet learned how to recycle. These first stars did more than shined. They altered their surroundings dramatically. Their intense radiation ionized nearby hydrogen. Their short lives ended in violent explosions. And in those final moments, they did something the universe itself could not do on its own. They created new elements: carbon, oxygen, silicon, ion, the raw materials for planets, for chemistry, for biology. Before the first stars, the universe was simple, smooth and sterile. After them, it was none of those things. Which means that if we want to understand how the universe transitioned from simplicity to structure, from darkness to complexity, we have to understand those first stars, not as a curiosity but as a turning point, because everything that came later depends on what happened here. And that brings us to a useful way astronomers organize this story: by generations, by chemical inheritance, by populations of stars that mark different eras in cosmic history. Once the first stars ignited, the universe crossed a line it could never uncross. For the first time since the Big Bang, matter was no longer just drifting and collapsing. It was being transformed. Inside, a star gravity does more than pull gas together. It raises pressure and temperature to extremes no planet could survive. In those conditions, atomic nuclei collide with enough energy to overcome their natural repulsion. They fuse, and when they fuse, they change identity. Hydrogen becomes helium. Helium becomes carbon. Carbon leads to oxygen, neon, magnesium, silicon. Each step releases energy, and that energy is what allows a star to shine for millions or billions of years. But from the universe's perspective, the light is almost a side effect. The real legacy of stars lies deeper in their role as chemical engines, because stars do not simply make elements, they distribute them. Low and intermediate mass stars shed material gently, exhaling enriched gas into space as they age. Massive stars take a more dramatic route. They end their lives in supernova explosions, releasing in seconds the elements they spent millions of years creating. Iron, nickel, and heavier nuclei are flung outward at thousands of kilometers per second, seeding their surroundings. This is how a chemically simple universe becomes a chemically diverse one. Not instantly, not uniformly, but cumulatively. Each generation of stars inherits the material processed by the ones before it. And with each cycle, the universe gains a little more complexity, more ways to cool gas, more solid material, more potential for structure. From this point onward, star formation is no longer starting from scratch. It is recycling. That distinction is crucial. A star like the Sun contains only a few % of heavy elements by mass, but that small fraction changes everything. It allows dust grains to form. It enables efficient cooling in collapsing gas clouds. It makes rocky planets possible. It makes chemistry rich enough for biology to even be conceivable. In other words, the universe did not become habitable all at once. It became habitable gradually as stars enrich their environment. And that brings us to a timeline that can be easy to overlook. The universe is roughly 13 to 14 billion years old. Our solar system formed about 5 billion years ago, which means that the material that became Earth had already been through multiple stellar generations before it ever assembled into a planet. The carbon in your cells did not come from a single star. It is the product of many stars over billions of years, each adding a small contribution to the cosmic inventory. This layered history allows astronomers to read chemical abundance like a fossil record. By measuring how much of each element a star contains, we can estimate when it formed relative to others. Older stars tend to be poorer in heavy elements. Younger stars are richer. Chemical composition becomes a timestamp. And once that pattern was recognized, astronomers realized they could organize stars into broad populations, not by age alone, but by inheritance, by how much previous stellar history is written into their atoms. This framework gives us a powerful tool. It allows us to infer what must have existed before the stars we see today, and it reveals a gap at the very beginning of the story, because even the oldest stars we can observe are already enriched. They are not pristine, which means they cannot be the first. To identify the universe's earliest stars, we need to look for something more extreme. Stars that formed before any recycling occurred, stars whose chemistry carries no memory of earlier generations. And that realization leads directly to a classification problem that astronomers solved in a surprisingly backward way. When astronomers began to sort stars by their chemical makeup, they quickly ran into an odd historical inconvenience. The naming scheme that emerged does not follow time in the direction you might expect. Stars like our Sun, rich in heavy elements and capable of forming complex planetary systems, were labelled Population 1. These are the stars most familiar to us, found primarily in the disk of the Milky Way, including the spiral arms where star formation continues today. Then came the discovery of older stars. These stars were poorer in heavy elements, not devoid of them, but noticeably lacking. Their spectra showed far less carbon, oxygen, silicon, and iron than the Sun. Many of them reside in the halo of the Milky Way, a roughly spherical distribution surrounding the galaxy's disk. Models of galactic formation suggest this halo assembled early before the disk took shape. These chemically primitive stars were labelled Population 2. The numbering was practical at the time, not prophetic. No one yet knew how many stellar generations might exist, but the chemical trend was unmistakable. The deeper astronomers looked into the halo, the fewer heavy elements they found. Some Population 2 stars contain as little as 1/100th the metal content of the Sun. A few drop even lower to 1,000th. These stars are ancient, among the oldest still shining in the galaxy, and yet they present a problem. Even the most metal-poor Population 2 stars are not chemically pristine. However small the fraction, their spectra still reveal elements heavier than helium, carbon, oxygen, iron, all present in trace amounts. And that fact matters, because if heavy elements are made only by stars, then the presence of any metals at all means these stars cannot be the first. They must have formed from gas that had already been enriched by an earlier generation. In other words, population 2 stars already have ancestors. This realization forced astronomers to confront a missing category, a hypothetical generation of stars that formed before any chemical enrichment occurred. Stars born from material left untouched since the Big Bang, stars made entirely of hydrogen and helium. To complete the sequence, these hypothetical objects were labelled population 3. The irony is hard to miss. The oldest stars get the highest number. Population 3 stars are not just older than population 2. They represent a fundamentally different starting point. They formed in a universe that had never experienced stellar death. A universe without dust, without metals, without any prior recycling. And that difference is not cosmetic. It changes the physics of star formation itself. Population 1 and 2 stars form in environments already shaped by billions of years of stellar evolution. Their birth clouds contain heavy elements that influence how gas cools, collapses, and fragments. Their masses are regulated by processes that depend on chemical complexity. Population 3 stars formed without any of that, which raises a crucial question. If population 3 stars ever existed, why do we not see them today? The universe is old, but not old enough for all stars to have died. Many low-mass stars can survive for trillions of years, far longer than the current age of the cosmos. If even a small fraction of population 3 stars were low-mass, they should still be shining somewhere. Hidden perhaps, but present. And yet despite decades of searching, none have been found. That absence is not a coincidence. It is a clue, and following that clue forces us to rethink what the first stars were actually like. In astronomy, absence can be as informative as presence. By the time population 3 stars were proposed, astronomers already understood something fundamental about how stars form. Whenever gravity assembles gas into stars, it does not produce a single mass. It produces a distribution, many small stars, fewer medium ones, and only a handful of giants. This pattern appears everywhere we look, in star-forming regions of the Milky Way, in nearby galaxies, in distant ones. The details vary, but the trend does not. Low-mass stars are overwhelmingly common, high-mass stars are rare, and that creates a powerful test. Low-mass stars burn their fuel slowly, extremely slowly. Some are so efficient that their lifetimes stretch into the trillions of years, longer than the current age of the universe by an order of magnitude. If any low-mass stars formed early in cosmic history, they should still be around today. They would be ancient, faint, chemically primitive, but unmistakably present. So astronomers went looking. They searched the halo of the Milky Way. They examined the most metal-poor stars known. They measured spectra with extraordinary precision, hoping to find an object with no heavy elements at all. They never did. Not one star has been found with a truly pristine composition. Every candidate, no matter how metal-poor, still carries the chemical fingerprints of earlier stellar activity. This absence forces a conclusion. If population 3 stars formed the way stars form today, we would see their low-mass survivors. The fact that we do not means the process must have been different. The first stars could not have included many low-mass objects. They must have formed almost exclusively as massive stars. This is not speculation, it is a deduction, a logical consequence of stellar lifetimes and what we observe today. Massive stars live fast and die young. The most massive burn through their nuclear fuel in just a few million years, some even faster. On cosmic timescales, they are brief flashes of activity, leaving no long-lived remnants behind. If population 3 stars were dominated by these giants, their disappearance makes sense. They would have formed, shone intensely, exploded, and vanished long before galaxies matured into their present forms. What they left behind was not themselves, but change. They altered the chemical composition of their surroundings. They ionized the intergalactic medium. They initiated the first wave of enrichment that allowed later generations of stars to form differently. This realization reframes the search. We are not looking for surviving population 3 stars. We are looking for environments where their influence is visible, but their successors have not yet erased the evidence. Places where the universe is still, chemically speaking, almost untouched. And that brings us to a deeper question. Why would the earliest star formation process favour massive stars so strongly? The answer lies not in history but in physics, in how gas behaves when the universe has not yet learned how to cool itself efficiently. To understand that, we need to examine what metals actually do during the birth of a star and what happens when they are completely absent. To understand why the first stars were so massive, we need to talk about something deceptively simple: cooling. Star formation is a competition between gravity and heat. Gravity pulls gas inward. Heat pushes it outward. A star is born only when gravity wins decisively enough for the gas to collapse to extreme densities and temperatures. In the modern universe, this process is moderated by heavy elements. Atoms like carbon, oxygen, and silicon are exceptionally good at radiating energy away. They emit light efficiently, allowing hot gas to cool as it collapses. Dust grains made from these same elements amplify this effect by providing surfaces that help gas shed heat even faster. Cooling allows gas clouds to fragment. Instead of collapsing into one enormous object, a cloud breaks apart into many smaller clumps. Each clump forms a star. This is why today's star-forming regions produce a wide range of stellar masses dominated by low-mass stars. But remove heavy elements and that entire system breaks down. In the early universe, gas clouds contained almost nothing but hydrogen and helium. These elements are poor radiators. They do not cool efficiently. As a result, collapsing gas stayed hot. Hot gas resists fragmentation. Instead of breaking into many small pieces, the cloud collapsed into just a few massive ones. Gravity had far fewer competitors. As material continued to fall inward, something else happened. In modern star formation, radiation pressure eventually pushes back. As a star grows brighter, its light exerts force on incoming gas. Heavy elements and dust absorb that light, transferring momentum and slowing further accretion. This sets an effective upper limit on stellar mass. But population 3 stars had no such braking system. With no metals to absorb radiation efficiently, light escaped more easily. Radiation pressure was weaker. Gas continued to fall inward. The star kept growing. Models of primordial star formation suggest masses tens, hundreds, even 1,000 times greater than the Sun. These were not just slightly oversized stars. They were extreme objects operating near the limits allowed by physics, and their size had consequences. Massive stars burn hotter. They emit enormous amounts of ultraviolet radiation. Their internal reactions proceed rapidly, racing through nuclear fuel that would last a smaller star billions of years. For the largest population 3 stars, lifetimes may have been measured in mere millions of years or less. From the perspective of cosmic history, they were brief, but during that brief existence they were transformative. Their radiation ionized surrounding hydrogen, changing the state of the intergalactic medium. Their deaths likely as powerful supernovae or direct collapses into black holes injected the first heavy elements into space. They marked the universe's transition from simplicity to diversity, and because they were so massive and so short-lived, none survived to the present day. This is why the first stars are invisible to us now. Not because they were rare, but because they were efficient. They did their work quickly, then disappeared. Which means that if we want to detect their existence, we cannot search for them directly. We have to search for their signatures, their light stretched by cosmic expansion, their chemical fingerprints or the conspicuous absence of them, their impact on the earliest galaxies. This is precisely the kind of evidence the James Webb Space Telescope was designed to pursue. But before we examine what Webb has found, we need to understand how such ancient light could possibly reach us at all. Because seeing the first stars is not just a matter of looking far away. It is a matter of looking back in time. When we talk about observing the first stars, it's easy to imagine a problem of distance. They are far away, so we need a bigger telescope. But distance is only part of the challenge. The deeper issue is time. Light does not travel instantly. It moves at a finite speed, which means that every time we look into space, we are also looking into the past. The farther away an object is, the earlier in cosmic history we see it. For the first stars that look back, time stretches to more than 13 billion years. During that time, the universe has not stood still. Space itself has been expanding, and as space expands, it stretches the light travelling through it. Wavelengths grow longer. High-energy light gradually loses energy as it journeys across the cosmos. This process is called redshift. The earlier stars were dominated by ultraviolet radiation. Their immense temperatures and masses made them prolific producers of high-energy light. But that light did not arrive at Earth as ultraviolet. Over billions of years of expansion, it was stretched step by step into the infrared. By the time it reaches us, it is no longer the light our eyes can see. This is the critical point. If you build a telescope optimized for visible light, the early universe will appear dim, distant, and largely inaccessible. Much of its story has been shifted out of view. The James Webb Space Telescope was designed with this in mind. Unlike earlier observatories, Webb is not primarily a visible light telescope. It is an infrared instrument. Its mirrors, detectors, and cooling systems were engineered to capture faint infrared signals with extraordinary sensitivity. In effect, Webb is tuned to the stretched-out whispers of the early universe. But even that is not enough. The first stars did not exist in isolation. They formed within the earliest galaxies collections of stars so young and so distant that their combined light is extraordinarily faint by the time it reaches us. Detecting them pushes technology to its limits, which means that Webb does not simply take pictures, it analyzes spectra. When light is spread out by wavelength, it forms a spectrum. Dark lines appear where specific elements absorb light. Bright features appear where gas emits it. These patterns act like fingerprints, revealing what elements are present and what physical conditions exist in the source. This technique allows astronomers to do something remarkable. They can determine the chemical composition of objects they can never touch, never sample, and never see directly in detail. From a smear of light collected across billions of years, they can tell whether carbon is present, whether oxygen exists, whether silicon or iron has left its mark, and just as importantly, they can tell when those fingerprints are missing. So when Webb observes a distant galaxy and finds light consistent with intense ultraviolet emission, but sees no evidence of heavy elements in its spectrum, the absence becomes meaningful. It suggests a population of stars unlike anything that forms today. Stars whose light is powerful, whose chemistry is primitive, and whose existence fits precisely where theory has long predicted the first stars should be. But there is still another obstacle. Even infrared light from the early universe is almost unimaginably faint. Without help, it would slip past our instruments unnoticed. That help comes not from technology but from gravity itself. To understand how we can detect such distant objects at all, we have to rely on a phenomenon predicted by general relativity and supplied conveniently by the structure of the universe. We have to rely on nature's own telescope. Long before humans built telescopes, the universe built one of its own. According to general relativity, mass does more than attract matter. It warps space itself, and when space is curved, light no longer travels in straight lines. It bends, it arcs, it can even be focused. This effect is known as gravitational lensing. When a massive object such as a cluster of galaxies lies between us and a distant source, its gravity distorts the space around it. Light passing through that region is deflected much like light passing through a glass lens. Depending on the alignment, the background object can appear stretched, duplicated, or dramatically magnified. For astronomers studying the early universe, this effect is not a curiosity. It is a necessity. The earliest galaxies are among the faintest objects that exist. Their light has travelled for more than 13 billion years, Along the way, it has been diluted by distance and stretched by expansion. By the time it reaches Earth, even the most powerful telescopes struggle to detect it. Gravitational lensing changes that a foreground galaxy cluster can amplify the light from a background galaxy by factors of 10^100 or more. Features that would otherwise be invisible rise above the noise. Signals that would be lost become measurable. In practical terms, this means that some of the most important observations made by the James Webb Space Telescope depend on a fortunate alignment of cosmic structures. The universe itself provides the magnification. Webb provides the sensitivity. Together they allow us to probe regions of space and time that would otherwise remain inaccessible. In the case of the potential population 3 detection, a massive galaxy cluster sits between us and the distant target. Its gravity bends and focuses the incoming light, effectively boosting the signal just enough for Webb to analyze it in detail. This is not an artificial enhancement. It is a physical consequence of mass and space-time. The data remain real. The photons remain genuine. They are simply easier to collect, and that distinction matters. Because gravitational lensing does not invent information, it reveals what is already there. When Webb examines the light from a lensed galaxy, it is still reading the original spectrum. The chemical fingerprints or their absence are preserved. The magnification allows astronomers to ask more precise questions, not different ones. This partnership between cosmic structure and human engineering highlights something subtle about modern astronomy. Many of our most profound discoveries are not the result of a single breakthrough, but of multiple effects working together. Expansion shifts light into the infrared. Massive stars flood the universe with ultraviolet radiation. Gravity bends space-time to magnify distant signals. And technology is built to catch what remains. Remove any one of these pieces and the observation fails. Which means that when we claim to see evidence of the first stars, we're not relying on one extraordinary coincidence. We're relying on a chain of well-understood physical processes, each reinforcing the next. But even with all of this assistance, interpreting the data is not straightforward, because magnified light is still just light, and when it reaches our detectors, we must decide what exactly produced it. Was it truly the combined glow of pristine stars? Or could something else be masquerading as their signal? To answer that, we have to look closely at what Webb actually observed and why the details matter. At the heart of this story is not an image, but a spectrum. When the James Webb Space Telescope observed the distant gravitationally lensed galaxy in question, it did not simply record a faint smudge of light. It dissected that light, spreading it into its component wavelengths. And it is within that breakdown that the most intriguing evidence appears. In galaxies we understand well, spectra are crowded. Carbon leaves its signature. Oxygen does the same. Silicon, nitrogen, iron. Each element imprints a recognizable pattern. These fingerprints are so reliable that astronomers can identify chemical compositions across billions of light years with confidence. But in this case, something was missing. The spectrum showed intense emission consistent with very hot massive stars, the kind that flood their surroundings with ultraviolet radiation. Yet the usual indicators of heavy elements were absent. No clear signatures of carbon, no oxygen lines, no silicon features. Not reduced, not weakened, missing. This is what makes the observation remarkable. Even the most metal-poor galaxies previously observed still show at least trace amounts of heavy elements. Complete chemical purity is not something astronomers expect to see once stars have been forming for any length of time, and that absence immediately narrows the possibilities. One explanation is radical but elegant. The light could be coming from stars formed before any chemical enrichment occurred. Stars composed almost entirely of hydrogen and helium. In other words, a population dominated by population 3 stars. If that interpretation is correct, this would represent the first observational evidence that such stars existed at all. But science does not move forward on excitement alone. Astronomers are trained to ask a second question immediately. What else could produce this signal? One alternative involves gas rather than stars. A cloud of primordial gas illuminated or heated in a way that mimics stellar emission could in principle generate light without heavy element signatures. Such clouds could be remnants of material left over from the Big Bang not yet processed by star formation. Distinguishing between these scenarios is difficult because at these distances telescopes collect only integrated light. Individual stars cannot be resolved. Everything blends together. That is why the claim is careful. The researchers do not say the first stars have been definitively found. They say the data are consistent with a galaxy dominated by metal-free stellar populations. They say the evidence is strong but not final. This is exactly how science should proceed. Extraordinary claims demand extraordinary verification, independent observations, additional spectra, alternative models tested and ruled out. What matters is not certainty but direction. For decades, population 3 stars were theoretical necessities. They filled a logical gap in our understanding of cosmic evolution. Now, for the first time, observations are approaching the sensitivity required to test that idea directly. And even if this particular object turns out not to host pristine stars, the fact that Webb can detect such extreme conditions at all is itself transformative. It means we are no longer speculating blindly about the universe's earliest chapters. We are reading them, which leads to the final question. If the first stars truly have been glimpsed not individually but through their collective imprint, what does that mean for our understanding of cosmic history? And more importantly, what does it mean for us? If this evidence holds the implications extend far beyond a single galaxy or a single discovery, the first stars would no longer be abstract objects that exist only in simulations and equations. They would become part of the observable universe, not as survivors but as ancestors whose influence can still be measured, because everything that followed depends on what they began. Before the first stars, the universe was chemically simple and structurally limited. After them, it was forever changed. Heavy elements spread into space. Gas cooled more efficiently. New generations of stars formed differently. Galaxies became more complex. Planets became possible. And eventually chemistry crossed a threshold. Atoms assembled into molecules. Molecules organized into systems capable of storing information using energy and maintaining structure. Biology did not emerge suddenly. It emerged from a long chain of physical prerequisites, each one dependent on the last. Population 3 stars sit at the beginning of that chain. They were not life-friendly. They were not stable. They were not long-lived. But they were essential. Without them, the universe would still be filled with hydrogen and helium drifting endlessly, unable to produce solid worlds or complex chemistry. In that sense, these stars were not just the first sources of light. They were the first agents of possibility. And this reframes how we think about our place in the universe. We often ask whether life elsewhere might resemble life on Earth, whether planets like ours are common or rare, whether biology is an accident or an inevitability. But all of those questions presuppose something deeper. They presuppose a universe capable of complexity at all. That capability was not guaranteed at the beginning. It had to be built, slowly, violently, through processes that cared nothing about outcomes, only about physical law. The atoms in your body do not trace their origins to one special star or one special moment. They trace back through countless stellar lives, through explosions and collapses, through environments that no longer exist. And at the root of that history lies a generation of stars that changed everything, then disappeared. The James Webb Space Telescope does not tell us who our ancestors were in any personal sense. It does something more fundamental. It shows us that the universe has a history, that complexity has a beginning, and that we are part of a story that started long before galaxies looked like galaxies. Whether this particular observation proves to be definitive or not, the direction is clear. We are no longer guessing about the universe's earliest chapters. We are beginning to observe them, and as we do, one conclusion becomes unavoidable. We did not arrive in a finished universe. We arrived in a universe that was shaped step by forces that operated long before we existed. and whose earliest actors are only now coming into view. If those first stars truly have been seen, then what Webb has shown us is not just where the universe came from, it is how a universe learned for the first time how to make something like us. When we talk about the origins of planets, life and complexity, we usually begin with creation, the birth of stars, the formation of galaxies, the emergence of worlds. But in the history of the universe, some of the most important events were not acts of creation at all. They were acts of destruction. The most consequential stars that ever existed did not shape the cosmos because they lived long, stable lives. They shaped it because they died violently, completely, and without leaving survivors. These were the first stars. They ignited in a universe that had never seen starlight before. They burned hotter and faster than anything that exists today, and within a few million years they were gone. No planets orbited them, no civilizations ever saw their light, and yet everything familiar to us depends on what happened when they disappeared. That is not an exaggeration. It is a physical statement. Before the first stars died, the universe could shine, but it could not build. It could illuminate space, but it could not create solid worlds. It could generate energy, but not structure. The raw ingredients for planets simply did not exist in usable form. Hydrogen and helium alone are not enough. You cannot make rock from them. You cannot form dust. You cannot assemble stable planetary systems. Those possibilities only emerge after stars begin to die. This is where the story takes an unexpected turn, because if the first stars were so important, then their deaths, not their births, were the moment when the universe crossed a permanent threshold. The transition from a luminous universe to a constructive one. The first stars were enormous by modern standards, hundreds of times more massive than the Sun. Their internal pressures and temperatures drove nuclear reactions at extraordinary rates. They lived fast and died young, and when they died, they did not fade quietly. Some exploded with such intensity that the star was completely torn apart, leaving nothing behind. Others collapsed inward so violently that they vanished from the visible universe altogether, forming the first black holes. Each outcome mattered. Each death reshaped the surrounding cosmos in a different way. Some deaths flooded space with newly forged elements, enriching vast regions in a single event. Others locked material away, delaying chemical progress, while planting the seeds of future cosmic structures. From these endings came diversity. From these endings came dust planets, oceans, and chemistry complex enough to support biology. And this reframes a common misconception. We often imagine that the universe became habitable as stars formed and galaxies assembled. In reality, habitability did not emerge from stability. It emerged from instability, from collapse, from explosion, from the destruction of objects that were never meant to last. The first stars did not make worlds while they lived. They made worlds when they died. Everything that followed, every rocky planet, every atmosphere, every molecule more complex than helium, traces back to those earliest stellar deaths. So if we want to understand how the universe learned to make planets, we cannot start with planets themselves. We cannot even start with galaxies as we know them. We have to start with an era when the universe could shine but not yet build. An era when light existed but structure did not. An era balanced on the edge of possibility, waiting for the right kind of destruction to unlock everything that came next. To see why those deaths mattered so much, we first need to understand what the universe lacked before they occurred, and why no amount of starlight alone could ever compensate for it. Before the first stars died, the universe existed in a strange intermediate state. It was no longer dark, but it was not yet capable of building worlds. Light filled space for the first time as massive stars ignited. Ultraviolet radiation poured into the surrounding gas. Entire regions of the cosmos were transformed from cold and neutral into hot and ionized. From a distance, the universe appeared active, energetic, alive. But beneath that glow, something essential was missing. Material. Not matter in general. There was plenty of matter, Vast oceans of hydrogen and helium stretched across space. Gravity was doing its work, pulling gas into clumps, feeding stars, shaping the earliest galaxies. What the universe lacked was structure-grade material. Hydrogen and helium are excellent fuels for stars, but they are terrible building blocks for planets. They do not form rigid solids at ordinary pressures. They do not condense into dust grains. They do not create the scaffolding required for complex chemistry. A universe made only of hydrogen and helium can shine brilliantly and still be incapable of producing a single rocky surface. This is a subtle but critical point. The first stars changed the energy state of the universe, but energy alone does not produce complexity. Complexity requires ingredients that can hold shape, store information, and participate in diverse chemical reactions. It requires elements that bind tightly, stack into lattices, and assemble into long-lived structures. Those elements did not yet exist in usable form. Before the first stellar deaths, there was no iron to anchor planetary cores, no silicon to build crusts, no carbon to form complex molecules, no oxygen to combine into water or minerals. The universe had brightness, but it had no architecture. Even the process of star formation itself was limited by this absence. In modern galaxies, collapsing gas clouds contain dust and heavy elements that radiate heat efficiently. Cooling allows gas to fragment, forming disks, clumps, and eventually planetary systems. But in the primordial universe, gas clouds struggle to cool. Without metals, heat lingered. Collapse was crude and inefficient. Stars could form, but refinement could not. And that distinction explains why the first stars were so extreme, why they grew so massive, why they burned so fast, why they were never meant to host planets. Planetary systems require patience, stability, recycling. The early universe had none of those. Even if a primitive disk of gas briefly formed around a first-generation star, it would have lacked solid grains. No seeds for planets to grow around. No way to transition from gas to rock. Any structure that appeared would have been fleeting, erased by radiation and stellar winds long before it could evolve. So while the first stars illuminated the cosmos, they did not civilize it. That required something far more violent. The universe needed a way to break stars apart, to tear their interiors open, to scatter newly forged elements into space where they could mix, cool, and recombine into something entirely new. It needed stellar death on a massive scale. Only then could the universe move beyond light and begin constructing matter in durable forms. Only then could dust appear. Cooling accelerate and disks rich enough to form planets emerge. In other words, the universe could not make planets until stars began to die, and not just any stars. It required the deaths of stars massive enough to manufacture heavy elements in abundance, and energetic enough to distribute them far beyond their birthplaces. To understand how that happened, we need to examine the different ways massive stars end their lives, because in the early universe not all stellar deaths were the same, and the path a star took at the end of its life determined how quickly the universe learned to build worlds. A star's life is defined by a balance. Gravity pulls inward, trying to crush the star under its own weight. Nuclear fusion pushes outward, releasing energy that resists collapse. As long as these two forces remain in equilibrium, a star shines steadily. For small stars, this balance can last for trillions of years. For massive stars, it cannot. The larger a star is, the harder gravity pulls. To resist that pull, fusion must proceed faster, and at higher temperatures, fuel is consumed at an extraordinary rate. What looks like abundance is in fact urgency. Massive stars live quickly because they must. At first, hydrogen fuses into helium. When hydrogen runs out, the star contracts, heats up, and ignites helium. That produces carbon and oxygen. As each fuel is exhausted, the star tightens its grip, raising temperatures further, unlocking new nuclear reactions. Carbon burns into heavier elements, oxygen burns into silicon. Silicon builds iron, and this is where the process ends. Iron does not release energy when it fuses, it absorbs it. Once a star's core is dominated by iron, fusion can no longer support the star against gravity. The balance breaks. What happens next depends on the star's mass. For stars only moderately massive, the core collapses suddenly. In less than a second it implodes, then rebounds violently. The outer layers crash inward, then are hurled back out in a catastrophic explosion known as a core collapse supernova. In these events, the star briefly outshines its entire host galaxy. Temperatures soar high enough to forge elements heavier than iron. Shockwaves rip through surrounding space, scattering newly created material across vast distances. But for the most massive stars, the kind that dominated the early universe, the story can take different turns. Some are so massive that even the energy of collapse cannot reverse the infall. The star does not explode. It simply disappears from view, collapsing directly into a black hole. Whatever elements were inside are locked away, removed from the surrounding environment. Others follow a more extreme path still. At enormous core temperatures, energy itself becomes unstable. Gamma rays convert into matter-antimatter pairs, reducing the pressure that supports the star. The core contract, violently igniting runaway nuclear reactions that tear the star completely apart. This is a pair instability supernova. In these explosions, nothing survives. No neutron star, no black hole. The entire star is unbound, its mass flung outward into space in a single overwhelming event. These were not subtle endings. They were decisive moments that determined how the early universe evolved, whether heavy elements were spread widely or hidden away, whether chemical enrichment accelerated or stalled, whether future stars and planets formed quickly or had to wait. The key insight is this: the universe did not receive its raw materials in a smooth, uniform process. It received them through punctuated catastrophes. Each massive star was a gamble. Its final fate shaped its surroundings in radically different ways. Some deaths seeded entire regions with metals in one moment. Others left little trace beyond gravity itself. And because the first stars were so massive, their deaths were among the most influential events the universe would ever experience. To understand how planets eventually became possible, we need to look more closely at these different endings, in particular at the most violent of them all, the explosions that did not just enrich the universe but rewrote it in a single instant. Among all the ways a star can die, this is the most extreme. A pair instability supernova is not an explosion layered on top of a collapse. It is a star destroying itself from the inside out, leaving nothing behind. This fate is reserved for stars of truly extraordinary mass, far larger than anything forming in the universe today. Stars so massive that the physics governing their cores begins to behave in unfamiliar ways. At the temperatures reached inside these primordial giants, the energy of light itself becomes unstable. High-energy gamma-ray photons are converted into pairs of matter and antimatter electrons and positrons. This conversion robs the star of radiation pressure, the very force holding gravity at bay. In an instant, the balance is lost. The core contracts violently, temperatures spike, nuclear reactions run out of control. Instead of settling into a collapse or rebounding into a conventional supernova, the star detonates. Completely. There is no remnant, no neutron star, no black hole. Every atom that once belonged to the star is hurled into space. And the scale of that release is difficult to overstate. A single pair instability supernova can eject tens of solar masses worth of newly forged elements. Carbon, oxygen, silicon, iron created in staggering quantities and dispersed across enormous volumes of space. Entire regions of the early universe could be chemically transformed by just one of these events. This is not enrichment by accumulation, it is enrichment by obliteration. For the first time, the universe received heavy elements not as rare contaminants, but as widespread ingredients. Gas clouds that were once chemically pristine suddenly contained the raw materials needed to cool, fragment, and reorganize in entirely new ways. Dust could form, cooling accelerated, smaller stars became possible. In a single moment the rules changed. But this pathway came at a cost. Pair instability supernovae are so energetic that they can sterilize their surroundings. Nearby, star-forming regions may be disrupted or destroyed. Gas can be blown away before it has time to collapse again. Chemical progress is rapid but uneven. Some regions are transformed almost instantly. Others remain untouched, lagging behind. This unevenness matters. It means that the universe did not evolve uniformly. Some pockets became chemically mature early. Others stayed primitive for much longer. The timeline for planet formation was not synchronized across space. And because pair instability supernovae leave no remnants, they also erase evidence of their own existence. No compact object remains to mark where the star once was. Only chemical fingerprints scattered across the interstellar medium. In that sense, these explosions are self-erasing events. They reshape the future while removing themselves from the present, yet not all first stars ended this way. Many followed a quieter, darker path, one that enriched the universe far more slowly but seeded something equally profound: the birth of the first black holes. To understand how those silent endings shaped the universe just as deeply, we need to examine the stars that collapsed inward rather than exploding outward. Not every massive star in the early universe ended in an explosion. For some, gravity won completely. These stars were so massive and their cores so dense that when nuclear fuel was exhausted, there was no rebound, no outward shock, no spectacular supernova. The collapse did not reverse itself. It continued. The star's core fell inward at a significant fraction of the speed of light. In seconds, space-time itself folded shut, an event horizon formed, and the star vanished from the visible universe, leaving behind the first black holes. From the outside, these deaths appeared almost anticlimactic. There was little light, little ejecta, little chemical enrichment. Compared to pair instability, supernovae direct collapse events seemed inefficient. They locked heavy elements away rather than distributing them. Vast quantities of material were removed from the surrounding environment, never to participate in future star or planet formation. At first glance, this appears counterproductive. If the universe needed metals to build planets, then stars that swallowed their own elements should have slowed that process down. And in many regions they likely did. But this is where the story becomes more subtle. These early black holes did not remain passive. Surrounded by dense gas, they began to accrete. Matter spiraled inward, heating up, releasing energy before crossing the event horizon. Even in the early universe, accreting black holes could become luminous objects emitting radiation that influenced their surroundings. They heated nearby gas. They altered pressure balances. They reshaped the dynamics of early galaxies. And over time, something else happened. These first black holes became seeds. As galaxies merged and grew, black holes merged with them. Mass accumulated. Accretion continued. What began as the collapse of a single massive star could over billions of years grow into the supermassive black holes we observe at the centers of galaxies today. In that sense, some of the earlier stellar deaths did not enrich the universe chemically. They enriched it gravitationally. They introduced compact objects capable of influencing galaxy evolution on enormous scales, objects that regulated star formation, redistributed gas, and shaped the environments in which planets would eventually form. This creates a tension in the early universe. On one side, explosive deaths rapidly spread metals, accelerating chemical maturity. On the other, silent collapses slowed local enrichment while laying the groundwork for large-scale structure. Both processes were necessary. Too many explosions and galaxies would be torn apart before stabilizing. Too many collapses and the universe would remain chemically primitive for too long. The balance between these two endings, obliteration and disappearance, determined how quickly different regions of the cosmos became capable of building planets. And that balance was not the same everywhere, which leads to a critical realization. The universe did not learn to make planets at a single moment. It learned at different times in different places depending on how the first stars died. To understand how uneven that process was, we need to examine the pace of chemical enrichment itself. How fast did metals spread? How quickly did conditions change? And how long did the universe remain divided between regions that could build worlds and regions that still could not? That question takes us to the tempo of cosmic evolution itself. Once the first stars began to die, the universe entered a phase of transition that was neither brief nor uniform. Chemical enrichment did not sweep across the cosmos like a wave. It spread unevenly, shaped by distance gravity and the specific ways stars ended their lives. Some regions were transformed rapidly. Others remained almost unchanged for hundreds of millions of years. The pace of change mattered. When a pair instability supernova exploded, it injected enormous quantities of heavy elements into its surroundings in a single event. Gas clouds nearby were suddenly rich enough to cool efficiently. Star formation in those regions shifted almost immediately. Smaller stars could form, disks became more stable, dust began to appear. In these pockets, the universe learned quickly, but where massive stars collapsed directly into black holes, enrichment stalled. Metals were trapped behind event horizons. The surrounding gas remained hot and primitive. Star formation continued, but it did so under conditions similar to those of the earliest era. The universe learned slowly there. This created a patchwork cosmos. Some early galaxies matured chemically at remarkable speed. Within a few generations of stars, they crossed the threshold required to form planetary systems. Others lagged behind, producing stars for long periods without ever acquiring enough heavy elements to build solid worlds. And this divergence had lasting consequences. Chemical enrichment is not just about quantity, it is about timing. Gas clouds that cool early fragment differently than those that cool late. Galaxies that stabilize early evolve along different paths than those constantly disrupted by radiation and collapse. Even today we see echoes of this process. Dwarf galaxies with low metal content, stellar populations with wildly different chemical histories, environments that never fully caught up to the cosmic average. The early universe set these trajectories in motion. What is striking is how quickly some regions may have crossed a critical boundary. Simulations suggest that in areas dominated by explosive stellar deaths, the universe could become chemically mature enough for rocky planet formation in less than a few 100 million years. That is a short time on cosmic scales. By contrast, regions dominated by direct collapse black holes may have taken far longer to reach the same state, if they reached it at all. The universe did not wait for consensus. It experimented. Different regions followed different evolutionary paths shaped by chance mass distribution and the local balance between explosion and collapse. Some pathways led rapidly toward complexity, others delayed it indefinitely. This diversity is not a flaw in the universe's design. It is a consequence of physics operating without foresight, and it highlights a key insight. Planets did not appear simply because enough time had passed. They appeared when conditions aligned, when enough metals existed, when cooling was efficient, when environments were stable enough to allow matter to organize itself into long-lived structures. The deaths of the first stars set those conditions in motion, but they did not guarantee outcomes. To move from enrichment to construction, the universe needed something smaller than supernovae, something quieter but just as essential. It needed dust, tiny grains invisible individually but collectively responsible for one of the most important transitions in cosmic history, the moment when gas began to behave like a building material rather than a fuel. And that moment marks the next turning point in how the universe learned to make worlds. In the story of cosmic evolution, it is easy to focus on the spectacular explosions that outshine galaxies, black holes that bend space-time, forces so extreme they defy intuition. But one of the most important turning points in the universe's ability to make planets came from something far smaller: dust. Not dust as we know it on Earth, but microscopic grains made from heavy elements. Carbon compounds, silicates, metal oxides assembled atom by atom in the aftermath of stellar death. Individually insignificant, collectively transformative. Before dust existed, gas behaved very differently. In a dust-free universe, gas clouds collapse slowly and inefficiently. Heat builds up and has nowhere to go. Fragmentation is suppressed. Structures remain large, hot and unstable. Star formation favors extremes. Dust changes that behavior almost immediately. These tiny grains are exceptionally good at radiating energy away. When gas collides with dust, heat is transferred and released as infrared light. Cooling accelerates. Temperatures drop. Gas clouds begin to fragment into smaller, denser clumps. This is not a minor adjustment, it is a phase change. With dust present, gas can settle into rotating disks. Those disks can persist long enough for material to collide gently rather than violently. Instead of everything rushing inward, matter begins to orbit, mix, and organize. Dust grains also act as seeds. Atoms stick to them. Molecules form on their surfaces. Larger aggregates grow through repeated collisions. What begins as microscopic particles gradually becomes macroscopic structure. Pebbles, rocks, planetesimals. Every rocky planet that has ever existed began this way. Without dust, none of it is possible. And dust does not form easily. It requires heavy elements, rapid cooling, and environments that are neither too violent nor too sterile. The first significant dust production likely occurred in the ejecta of early supernova, where temperatures dropped quickly enough for solids to condense before radiation could tear them apart. This means that not all stellar deaths contributed equally. Explosions that dispersed metals widely also created the conditions for dust formation. Collapses that locked material away did not. Regions dominated by one type of death became dusty early. Others remained clean for much longer. Once again, the universe diverged. In dust-rich regions, star formation changed character. Lower-mass stars became common. Lifetimes lengthened. Stable environments emerged. In dust-poor regions, star formation remained harsh and top-heavy, delaying the transition to planetary systems. This is why dust, despite its small scale, represents one of the most decisive thresholds in cosmic history. It marks the moment when matter stopped behaving purely as fuel and began behaving as material. The moment when the universe acquired the ability to build surfaces. From that point on, planets were no longer hypothetical. They were inevitable given enough time and the right conditions. The first dust did not create worlds immediately, but it made their existence physically possible for the first time. And once that possibility existed, the clock toward planetary formation began ticking. The next question is how long it took for those early dusty environments to cross the final threshold from raw material to fully formed rocky worlds. To answer that, we have to look at when the universe first became capable of assembling planets at all. Once dust existed in meaningful quantities, the universe entered a new phase of construction. For the first time, gas clouds could cool efficiently, fragment predictably, and settle into long-lived disks around newly forming stars. These disks were not just reservoirs of gas. They were mixed environments rich in dust grains that collided, stuck, and grew. This is the critical distinction. Stars can form without dust. Planets cannot. In dust-rich disks, gravity and motion work together rather than in opposition. Particles orbit a central star, encountering one another at velocities low enough to allow aggregation instead of destruction. Over time, grains grow into pebbles, pebbles into rocks, rocks into kilometre-scale planetesimals. From there, gravity takes over. Once objects reach sufficient mass, they begin to dominate their surroundings. They sweep up material, clear path through the disk, and accelerate their own growth. What begins as microscopic debris evolves into fully fledged planetary bodies. The physics of this process is well understood. What remains uncertain is when it first became possible. Models suggest that once a region of the universe reached a modest threshold of metallicity, just a small fraction of the Sun's heavy element content rocky planet formation could proceed. The universe did not need to be chemically rich by modern standards. It only needed to be not pristine, and that threshold may have been crossed surprisingly early. In regions heavily enriched by the explosive deaths of massive stars, conditions suitable for rocky planets could have emerged within a few 100 million years after the Big Bang. That is billions of years earlier than the formation of Earth. This does not mean that such planets were common everywhere. Far from it. The early universe was chaotic. Radiation levels were high, supernovae were frequent, many environments were hostile to long-term stability, but possibility is not the same as prevalence. The key point is that the universe acquired the ability to make rocky worlds long before it made ours. Some of those early planets may have been short-lived. Others may have formed in environments too violent to sustain complex chemistry for long. But from a physical standpoint, the barrier had been crossed. The universe no longer lacked the ingredients. It had dust. It had metals. It had disks. It had time. From this moment onward, planet formation was no longer forbidden by physics. It became a question of environment, timing, and chance. And this reframes how we think about Earth. Our planet did not arrive as soon as it could have. It arrived when conditions in our region of the galaxy had become unusually calm and stable, long after the universe learned how to build worlds but before it exhausted its capacity to do so. Which raises a deeper question. If rocky planets were possible so early, why did life not appear immediately everywhere? Why does the universe seem to have waited? The answer lies not in the existence of planets alone, but in the balance between creation and destruction, a balance that was not yet settled in the early cosmos. To understand that balance, we need to examine the narrow window in which habitability becomes feasible, and how easily it can be disrupted. That takes us to one of the most delicate phases in cosmic history. The ability to build planets does not automatically lead to the ability to host life. Between those two milestones lies a narrow and fragile window defined not by chemistry alone, but by balance. A balance between creation and destruction, between stability and violence, between environments that nurture complexity and those that erase it before it can take hold. In the early universe, that balance was difficult to achieve. The same massive stars that enrich space with heavy elements also made it hostile. Their radiation was intense. Their deaths were frequent. Supernovae erupted, regularly flooding nearby regions with high-energy particles capable of stripping atmospheres and sterilizing surfaces. In some regions, chemical maturity arrived quickly, but stability did not. Planets may have formed only to be bombarded relentlessly. Atmospheres could be lost before they had time to settle. Oceans, if they existed at all, would have been transient. Complex chemistry requires not just ingredients but continuity. Too much enrichment too quickly can be just as limiting as too little. At the other extreme, regions dominated by direct collapse black holes remained comparatively calm but chemically poor. Star formation continued, but planets struggled to emerge. Without sufficient metals and dust, rocky worlds were rare or non-existent. These opposing regimes created a cosmic tension. Violent regions progressed chemically but remained unstable. Quiet regions were stable but chemically delayed. Habitability requires a compromise. It requires an environment enriched enough to build solid worlds yet calm enough to allow those worlds to persist. It requires time between catastrophic events. Time for atmospheres to accumulate. Time for surfaces to cool. Time for chemistry to explore complexity. Astrophysicists sometimes refer to this as a kind of Goldilocks epoch in cosmic history. Not too early, not too violent, not too chemically primitive. A period when the universe locally became just right. This window did not open everywhere at once. It appeared first in select regions, galaxies, or substructures where enrichment had occurred, but where massive stellar deaths became less frequent, where star formation slowed into a steadier rhythm, where disks and planets were not constantly reset by catastrophe. Only then could complexity persist long enough to matter. This perspective challenges a common assumption. Life did not simply wait for planets to appear, it waited for the universe itself to calm down. The early cosmos was energetic, productive, and creative, but also unstable. Over time, as the most massive stars disappeared and star formation shifted toward lower masses, the universe gradually became a quieter place. And in that quiet, new possibilities emerged. This does not mean that life could not have arisen earlier. It means that early opportunities were rare, fragile, and easily erased. The universe experimented but did not yet commit. The deaths of the first stars created the ingredients for habitability, but it took time and restraint for those ingredients to assemble into lasting systems. Understanding this window helps explain why Earth formed when it did. Not at the earliest possible moment, but at a time when chemical richness and environmental stability finally overlapped. Which brings us to the final realization of this story. We do not live at the beginning of cosmic history, but we also do not live at its end. We live in the aftermath of a long sequence of stellar deaths that gradually taught the universe how to build worlds and how to preserve them. To see what that means for us, we have to step back and look at where we stand in that chain of consequences. Every rocky planet, every ocean, every atmosphere capable of sustaining chemistry exists in the wake of stellar death. This is not metaphor, it is causality. The universe did not begin with worlds. It began with simplicity, hydrogen, helium, expansion, time. For hundreds of millions of years it could shine but not construct. Energy existed but material complexity did not. That changed only when the first stars ended their lives. Some tore themselves apart completely, scattering the elements needed to cool gas-formed dust and assemble solid surfaces. Others collapsed inward, planting gravitational seeds that shaped galaxies for billions of years to come. Together, these deaths transformed the universe from a place that merely existed into one that could build. Everything familiar to us follows from that transition. The silicon beneath your feet, the iron at the center of your planet, the oxygen bound into rock and water, none of it was present at the beginning. All of it is the residue of stars that no longer exist. Even Earth's long delay makes sense in this context. Our planet did not form at the first possible moment. It formed when enrichment, stability, and time finally aligned in our region of the galaxy, long after the universe learned how to make planets, but before it exhausted its capacity to do so. We are not early, we are not late, we are well downstream, and this perspective reframes how we think about cosmic history. The first stars were not important because they illuminated the darkness. Light alone changes little. They were important because their deaths altered the material rules of the universe. They introduced irreversibility. Once heavy elements existed, the universe could never return to its original simplicity. From that point forward, complexity was not guaranteed, but it was possible. Galaxies evolved. Star formation slowed. Violent events became less frequent. Stable environments emerged. And in some of those environments, chemistry crossed a threshold that allowed systems to persist, adapt, and eventually observe themselves. We are part of that outcome, not the goal of the process, but a consequence of it. The universe did not know it was making planets. It did not know it was creating conditions for life. It followed physical law, and complexity emerged as a side effect. When we look back toward the first stars, we're not just studying distant objects, we are reconstructing the sequence of events that made our own existence physically possible. And when we recognize that something subtle changes, the universe no longer feels like a place that suddenly produced worlds out of nowhere. It feels like a system that learned slowly, violently, and without intent how to assemble them, one stellar death at a time. We do not live in the beginning of that story, but we live in its aftermath, and the farther we look back, the clearer it becomes that everything we call familiar was born not from creation alone, but from destruction that came before it. The universe began in brilliance. In its earliest moments, space was filled with energy so intense that light itself could not travel freely. Everything was hot, dense, and luminous. Matter and radiation were tightly coupled, locked together in a glowing, opaque state. And yet, not long after that radiant beginning, the universe went dark. For hundreds of millions of years, there were no stars, no galaxies, no visible sources of light. This is one of the most counterintuitive chapters in cosmic history. How does a universe that begins in fire and light descend into darkness? Why would a cosmos born bright remain unlit for so long? The answer is not a failure of physics, it is a consequence of it. The early universe did not go dark because it lacked energy. It did not go dark because matter disappeared. It went dark because the conditions required to produce light had not yet been met. Light in an astronomical sense is not something that simply exists. It must be generated, sustained, replenished, and that requires structure. Stars are not inevitable outcomes of a hot beginning. They are delicate constructions dependent on gravity cooling time and the slow amplification of tiny imperfections. None of those processes happen instantly. After the universe cooled enough for atoms to form, light was finally able to travel freely through space. For a brief moment, the cosmos became transparent. Radiation streamed outward in all directions, carrying a snapshot of the universe at that time. Then something unexpected happened. That light kept moving, but no new light replaced it. The universe expanded. Radiation thinned. Space grew larger and colder. And without stars to replenish the glow, darkness returned not as emptiness but as silence. This period is known as the Cosmic Dark Ages. The name can be misleading. It suggests stagnation, inactivity, nothingness. In reality, the Dark Ages were anything but empty. Matter was still there. Gravity was still working. The universe was busy preparing itself for the return of light. But preparation takes time. The universe had to cool further. It had to allow matter to clump. It had to let gravity amplify the smallest irregularities left behind by the Big Bang. Only then could the first stars ignite. From our perspective, this delay feels enormous. Hundreds of millions of years with no stars seems excessive. But the universe was not in a hurry. It was following physical law, not a timetable. And that law required patience. If stars had formed too early, they would have failed. Gas would not have cooled efficiently. Structures would have collapsed and unraveled. Light would have flickered briefly, then vanished again. The darkness was not an accident. It was a prerequisite. The universe needed time to organize itself, to transition from a uniform glow into a structured system capable of sustaining light sources that could last, multiply, and reshape their surroundings. Only after that long night could the first stars appear, and with them the beginning of galaxies, planets, and everything that would follow. To understand why that night lasted so long, we need to go back to the moment when the universe first became transparent and examine what changed and what did not, when light was finally allowed to travel freely. That takes us to the first time the universe ever let itself be seen. To understand why the universe went dark, we have to revisit the first moment when light was finally allowed to move freely. In the earliest phase after the Big Bang, the universe was not just bright, it was opaque. Matter and radiation were locked together in a dense, energetic plasma. Photons could not travel far before colliding with charged particles. Light existed, but it was trapped. As the universe expanded, it cooled. Eventually it crossed a critical threshold. Protons and electrons combined to form neutral hydrogen atoms. This event is known as recombination, though it was the first time such combinations ever occurred. With electric charges neutralized, photons were suddenly free to travel long distances without constant interference. For the first time, the universe became transparent. Light streamed outward in all directions, carrying with it a snapshot of the cosmos at that moment. Today we observe that ancient radiation as the cosmic microwave background, a faint uniform glow that fills the sky and marks the earliest image we can ever see. From a distance, this might look like the universe turning on its lights, but that impression is misleading. The cosmic microwave background is not sustained illumination. It is residual light, a fading echo of a moment when conditions briefly allowed radiation to escape. Once released, those photons simply continued on their paths, stretching and cooling as space expanded. No new light sources replaced them. At this stage, the universe contained atoms but no stars. Gas was everywhere, but it was diffuse and cold. Gravity had not yet gathered matter into dense enough concentrations to ignite nuclear fusion. The universe was transparent but unlit. This distinction is crucial. Transparency does not create light. It only allows light to pass through, without objects capable of generating energy continuously. Darkness is inevitable no matter how luminous the beginning was, and so the universe entered a prolonged quiet phase. The cosmic microwave background faded from visible light into infrared, then to microwaves. Expansion diluted its energy further. What had once been a brilliant glow became a faint background signal detectable only with sensitive instruments. Meanwhile, nothing replaced it. No stars yet existed to shine. No galaxies had formed to host them. Space was filled with neutral hydrogen drifting through vast regions governed primarily by gravity and time. This was not a collapse back into chaos. It was a pause, a necessary interval between a hot beginning and a structured universe. During this interval, the universe was not idle. It was evolving in ways that were invisible to light. Density variations were growing. Matter was slowly responding to gravitational attraction. Regions slightly denser than average were becoming more pronounced, but none of this produced illumination. Light had escaped, but structure had not yet caught up. From the outside, the universe appeared dark. From within, it was reorganizing itself, laying the groundwork for the next transformation. The return of light would require something new. Not leftover radiation, but engines capable of generating energy for millions of years at a time. It would require stars, and stars, unlike photons, do not emerge instantly. They demand patience from the universe, time for gravity to gather matter and conditions precise enough to allow collapse without immediate disruption. To see why that process took so long, we need to understand what the universe looked like during this dark interval. Not in terms of light, but in terms of matter. That means examining the so-called cosmic dark ages as they actually were rather than as their name suggests. The phrase cosmic dark ages invites the wrong mental picture. It suggests emptiness, stillness, a universe doing nothing while it waits for stars to appear. In reality, the dark ages were one of the most active periods in cosmic history, just not in ways that produced light. During this era, the universe was filled with matter. Vast amounts of it, almost all in the form of neutral hydrogen and helium, spread thinly across expanding space. This gas was not glowing. It was cold, invisible, and difficult to detect, but it was far from static. Gravity was at work everywhere. Tiny differences in density imprinted during the Big Bang began to matter. Regions that were just slightly denser than average exerted slightly stronger gravitational pull. Over time, those regions attracted more matter, and as they did, the contrast between dense and sparse areas slowly increased. This process was not dramatic. It did not involve explosions or sudden collapse. It unfolded gradually over tens and then hundreds of millions of years. But it was relentless. Gravity does not rush. It accumulates. What made this era challenging for star formation was not a lack of matter, but a lack of efficient cooling. As gas fell into denser regions, it heated up. Hot gas resists collapse. To form stars, gas must lose energy, cool down, and compress further. In the modern universe, this cooling is assisted by heavy elements and dust. During the Dark Ages, neither existed. Hydrogen and helium are poor radiators. They struggle to shed heat efficiently, especially at low densities. As a result, gas clouds stalled. They gathered mass but could not easily collapse into the compact structures required to ignite nuclear fusion. Gravity was pulling inward, but thermal pressure pushed back. The balance tipped only very slowly. This is why the Dark Ages lasted so long. Not because the universe lacked gravity, not because matter was absent, but because the physics of cooling worked against rapid progress. Still structure was forming. Dark matter, an invisible component that does not interact with light, played a crucial role here. It began clumping first, forming gravitational wells that ordinary matter could fall into. These wells did not shine, but they provided the scaffolding around which future stars and galaxies would assemble. Gas followed dark matter's lead. Over time, hydrogen accumulated inside these invisible structures. Densities rose, temperatures increased, and eventually in the deepest of these wells, conditions approached a tipping point. The Dark Ages were not a delay imposed by chance. They were a filtering process. Only regions with the right combination of mass density and cooling ability could progress to the next stage. Everything else remained diffuse. From our perspective, this long darkness can feel excessive, but from the universe's perspective, it was necessary. If collapse had occurred too quickly, structures would have been unstable. If cooling had been too efficient, fragmentation would have prevented the formation of the massive stars needed to transform the cosmos. The universe was calibrating itself, learning how to build stars under the most primitive conditions imaginable. And once that calibration was complete, the first stars would ignite not everywhere, but in select regions where gravity had quietly done its work. To understand why those regions existed at all, and why they formed where they did, we have to look even deeper into the smallest imperfections left over from the universe's birth, the tiny asymmetries that made all structure possible. If the universe had been born perfectly smooth, nothing you see today would exist. No stars, no galaxies, no planets. In a perfectly uniform universe, gravity would have had nothing to work with. Matter would be spread evenly, pulling equally in all directions, cancelling itself out. Expansion would simply dilute everything forever. But the universe was not perfect. In the earliest moments after the Big Bang, tiny irregularities were imprinted into the fabric of space. Variations in density so small they differed by only one part in 100,000. To the naked eye, or even to most instruments, these differences would be invisible. To gravity, they were everything. Regions that were slightly denser exerted slightly stronger gravitational pull. Over time, that extra pull mattered. Matter drifted inward slowly at first, then more decisively as density increased. The denser a region became, the more efficiently it could attract additional material. This feedback loop is the foundation of all cosmic structure. What makes these imperfections remarkable is not their size, but their persistence. They survived the violent expansion of the early universe. They were carried forward as space stretched and cooled. And once the universe became transparent, they were free to grow without interference from radiation pressure. The cosmic microwave background preserves a snapshot of these fluctuations, a faint pattern of warm and cool spots that map the earlier seeds of structure. Every galaxy you see today can trace its ancestry back to one of those tiny deviations. During the Dark Ages, these imperfections began to diverge dramatically in their consequences. Most regions remained close to average. They expanded, cooled, and thinned out, but a small fraction, those born just slightly denser, crossed a critical threshold. Gravity began to dominate over expansion locally. Matter collected. At first, this collection was subtle. Gas drifted inward at walking pace on cosmic scales. There were no sudden collapses, no flashes of light, but over millions of years these regions became distinct environments, protostructures forming in an otherwise featureless cosmos. These early concentrations were not yet galaxies, they were not even luminous, but they were different. They were places where time mattered. Given enough time, these regions would grow dense enough to trap gas-rays temperatures and eventually ignite stars. Regions that started out just a little denser than their surroundings would end up fundamentally transformed. This sensitivity to initial conditions is a recurring theme in cosmic history. Small differences early on produce enormous differences later. A universe that begins almost uniform evolves into one filled with structure simply because gravity never forgets even the slightest imbalance. But there is another ingredient that made these imperfections effective. An invisible one. The density fluctuations alone were not enough to form stars quickly. Something else had to lead the way. Something that could clump early, interact gravitationally, and ignore the limitations that held ordinary matter back. That something was dark matter. To understand why the universe did not remain dark forever, we have to examine the role of this unseen component, the architect that shaped the scaffolding of everything that would eventually shine. Long before the first stars ignited, an unseen structure was already taking shape. Dark matter does not emit light. It does not absorb it. It does not interact with radiation in any way we can detect directly. And yet it dominates the mass budget of the universe. By a wide margin, This matters because gravity does not care whether matter is visible. Dark matter began clumping early, even while ordinary matter was still tightly coupled to radiation. It felt gravity's pull without resistance. It did not heat up. It did not glow. It simply accumulated. As the universe expanded and cooled, dark matter formed dense concentrations known as halos. These halos acted as gravitational anchors, pulling in surrounding gas once atoms became neutral and free to move independently. In effect, dark matter built the framework of the universe in advance. By the time ordinary matter was ready to collapse, the scaffolding was already there. Gas fell into these dark matter halos drawn inward by gravity. But unlike dark matter, gas could heat up. As it compressed, its temperature rose, and without efficient cooling mechanisms, that heat became a barrier to further collapse. This is where the partnership and tension between dark matter and ordinary matter becomes clear. Dark matter could form structure quickly, but it could not shine. Ordinary matter could shine, but it struggled to collapse. The early universe depended on their interaction. Halos that were too small could not trap gas effectively. Thermal pressure pushed material back out. Only halos above a certain mass threshold could retain gas long enough for densities to build and temperatures to reach the levels required for star formation. This threshold was not arbitrary. It was set by physics. Too little mass and gravity loses. Too much mass and collapse proceeds, but slowly. As a result, the first stars did not form everywhere. They formed only in the most massive early halos in regions where dark matter had assembled enough mass to overcome the limitations of primordial gas. This selective process explains why the Dark Ages were patchy rather than uniform. Some regions progressed towards star formation relatively early, others lagged far behind. The universe did not light up all at once. It ignited in isolated pockets scattered across vast distances, and this uneven ignition had lasting consequences. The first stars shaped their surroundings dramatically. Their radiation ionized nearby gas. Their deaths enriched local environments with heavy elements. Regions that hosted early star formation evolved faster. Regions that did not remained chemically primitive. In this way, dark matter did more than organize matter. It set the tempo of cosmic history. By determining where stars could form first, it dictated where light would return, where galaxies would begin assembling, and where the universe would first take steps toward complexity. Without dark matter, gravity alone would have struggled to create structure before expansion diluted matter beyond recovery. The universe might have remained dark indefinitely, not because stars were impossible, but because they were too slow to form. Dark matter accelerated the process just enough. It did not create stars, it made star creation possible. And once the first stars ignited within these dark halos, the universe entered a new phase, one defined not by preparation but by ignition. To understand why that ignition still took hundreds of millions of years, even with dark matter's help, we have to examine the final obstacle the universe had to overcome: the physics of cooling, the reason gravity alone was not enough, and why the first stars required such patience from the cosmos. By the time dark matter halos had assembled, the universe had solved only half of the problem. Gravity had created places where matter could gather, but gathering matter is not the same as igniting stars. For that, the universe needed cooling. As gas falls into a gravitational well, it heats up. The conversion of gravitational energy into thermal energy is unavoidable, and hot gas resists further collapse. If that heat cannot be removed efficiently, the process stalls. In the modern universe, this obstacle is relatively easy to overcome. Heavy elements and dust radiate energy away with remarkable efficiency. Gas cools quickly, fragments into smaller clumps, and forms stars across a wide range of masses. The early universe had none of those advantages. Primordial gas was composed almost entirely of hydrogen and helium. These elements are poor radiators. At the low densities typical of early halos, they struggle to emit energy fast enough to cool collapsing gas. This created a bottleneck. Gas could fall inward, but only to a point. Beyond that, rising temperature counteracted gravity. collapse slowed dramatically. Instead of racing towards star formation, matter hesitated. For hundreds of millions of years, the universe sat near this threshold. Cooling did occur, but inefficiently. The primary mechanism available was molecular hydrogen. Under the right conditions, small fractions of hydrogen atoms combined into H2 molecules. These molecules could radiate energy away more effectively than atomic hydrogen, allowing gas to cool further. But forming molecular hydrogen was itself difficult. It required rare interactions. It was easily destroyed by radiation, and it formed in tiny quantities, enough to matter but barely. As a result, star formation in the early universe was slow, selective, and fragile. Only the most massive halos with the deepest gravitational wells could compress gas enough for molecular cooling to become effective. This explains the long delay. The universe was not waiting idly for stars to appear. It was struggling against the limits imposed by its own chemistry. Gravity pushed inward. Heat pushed back. Cooling lagged behind. Only when conditions aligned, sufficient halo mass, enough molecular hydrogen, enough time could collapse proceed to completion, and when it did so decisively. The first stars did not form gently. They formed under extreme conditions in environments that favoured rapid collapse once the cooling barrier was breached. Gas that had resisted collapse for eons suddenly gave way, funneling inward to ignite nuclear fusion. This is why the first stars were so massive. The universe did not form small stars first and large stars later. It did the opposite. Early star formation was coarse and inefficient, producing giants because fragmentation was suppressed. The long darkness was the price of this inefficiency. But once the cooling problem was solved even locally, the consequences were immediate. Light returned to the universe not as a uniform glow, but as isolated beacons piercing the cosmic night. The first stars ignited in scattered pockets, each one dramatically altering its surroundings. And with that ignition, the universe crossed another irreversible threshold. The return of light did not simply end the Dark Ages. It began a transformation that would change the state of nearly all matter in the cosmos. To understand that transformation, we need to follow what happened when the first stars turned on not just locally but on cosmic scales. That takes us to the moment when light did more than illuminate. It reshaped the universe itself. When the first stars finally ignited, the universe did not brighten gently. It changed abruptly. These earlier stars were unlike anything that forms today. They were massive, extremely hot and intensely luminous. Their surface temperatures drove nuclear reactions at extraordinary rates, producing vast amounts of ultraviolet radiation. In a universe that had been dark for hundreds of millions of years, even a small number of such stars made an outsized impact. Light returned, but it returned unevenly. Each star lit up only its immediate surroundings. Vast regions remained untouched, still dark and neutral. The cosmos did not switch on like a lamp. It flickered into visibility in isolated pockets separated by enormous distances. But the light itself was only part of the story. Ultraviolet radiation from the first stars carried enough energy to tear electrons away from hydrogen atoms. Neutral gas became ionized once again, reversing the state the universe had entered after recombination. Wherever this radiation reached, it altered the physical behavior of matter. Ionized gas behaves differently. It couples more strongly to radiation. It changes how heat is transported. It reshapes how future stars can form. In this way, the first stars did not merely illuminate space. They began to modify the universe's fundamental conditions. Their influence extended far beyond their short lifetimes. As these stars burned through their fuel and died often violently, they left behind environments transformed by both radiation and chemistry. Gas that had been neutral for hundreds of millions of years was now energized. Regions that had resisted collapse were suddenly altered in ways that could either promote or suppress further star formation. This created feedback. In some areas, radiation heated gas and pushed it away, delaying new stars from forming. In others, shockwaves and compression triggered additional collapse. The return of light was not purely constructive or destructive. It was complex, and it was cumulative. Each new star added to the background radiation field. Each death enriched local gas with heavy elements. Over time, isolated pockets of light began to overlap. The universe was no longer simply dark or bright. It was transitioning. This marks the true end of the Dark Ages, not when the first star formed, but when their combined influence began to matter on large scales. The return of light was a process, not a moment, and as it progressed, it led to one of the most sweeping transformations the universe has ever experienced. A transformation that changed the state of nearly all ordinary matter. To understand that change, we have to follow the spread of ionizing radiation across cosmic distances. We have to examine how the first stars did something even more profound than shining. They rewrote the electrical state of the universe itself. As the first stars multiplied, their influence began to extend far beyond the regions where they were born. Each massive star poured out ultraviolet radiation capable of ionizing hydrogen. Individually, these stars carved out small bubbles of ionized gas around themselves. Inside those bubbles, electrons were stripped from atoms. Temperatures rose and the physical behavior of matter changed. At first, these bubbles were isolated. They expanded slowly, bounded by the limits of radiation and distance. Most of the universe remained neutral and dark, but star formation did not stop with the first generation. New stars ignited in neighboring halos. Galaxies, still primitive and chaotic, began producing clusters of massive stars rather than isolated ones. As that happened, something remarkable occurred. The ionized regions began to overlap. What started as scattered pockets of energized gas grew into connected networks. Boundaries dissolved. Ionization fronts swept outward, transforming ever larger volumes of the universe. This process is known as cosmic reionization. Reionization was not instantaneous. It unfolded over hundreds of millions of years. Some regions were ionized early, others much later. Dense pockets of gas resisted the advance longer than diffuse regions. The universe transitioned gradually unevenly from a mostly neutral state to one dominated by ionized hydrogen. But once complete, the change was permanent. After reionization, the universe never returned to its earlier neutral condition. The average state of intergalactic gas was fundamentally altered. The background radiation field became persistent. The environment in which galaxies evolved was no longer the same as it had been during the Dark Ages. This transformation had far-reaching consequences. Ionized gas responds differently to gravity. It resists collapse more strongly. Small dark matter halos that might have formed stars before reionization were suddenly deprived of their fuel. Gas was heated and expelled. Star formation in low-mass systems was suppressed. In effect, reionization imposed a new rule on the universe. Only sufficiently massive structures could continue forming stars efficiently. The era of easy ignition was over. From this point forward, galaxy growth favored larger systems with deeper gravitational wells. This is why the earliest galaxies look so different from those that formed later. Before reionization, star formation could occur in relatively small halos. After reionization, those same halos struggled to retain gas. The population of galaxies was reshaped by a process driven not by gravity alone, but by radiation. Reionization also left observable fingerprints. The cosmic microwave background carries subtle signatures of this era. Quasar spectra reveal the gradual disappearance of neutral hydrogen absorption. Modern observations allow astronomers to reconstruct the timing and progression of this transformation with increasing precision. What these observations tell us is that darkness did not simply end when the first stars appeared, it ended when enough stars had formed to change the universe globally. Reionization marks the moment when light stopped being local and became cosmic, when the universe as a whole crossed from a state of preparation into a state of sustained activity. And with that transition, the stage was set for the next major development. The assembly of galaxies not as isolated experiments, but as enduring structures shaped by the conditions created during this long journey out of darkness. To understand what those early galaxies were like, we need to look at a time when galaxies existed in name but not yet in familiar form. A time before spiral arms, before stable disks, before the quiet rhythm we see today. a time of galaxies before galaxies. When we picture a galaxy, we usually imagine something familiar, a graceful spiral, a glowing disk, billions of stars arranged into a stable, long-lived structure. But the first galaxies looked nothing like that. In the era just after Reionization began, galaxies were not elegant systems. They were fragile experiments, small chaotic collections of stars embedded in turbulent clouds of gas and dark matter. They formed, merged, disrupted, and reformed repeatedly. These early structures are sometimes called proto-galaxies, but even that name risks implying too much order. They were irregular, clumpy, violently active. Star formation occurred in bursts rather than steady rhythms. Massive stars dominated, flooding their surroundings with radiation. Supernovae were frequent enough to reshape entire systems. Gas was expelled, then pulled back in, then expelled again. Nothing about these early galaxies was calm. They were also small. Compared to the Milky Way, the first galaxies contained only a tiny fraction of the mass. Many were closer in scale to modern dwarf galaxies, but far less stable. Their gravitational wells were shallow, making them highly sensitive to feedback from star formation and radiation. Reionization intensified this instability. As the intergalactic medium became ionized and heated, gas struggled to fall into small halos. Some proto-galaxies were effectively starved. Others survived only because they merged with neighbours, growing larger and deeper gravitational wells in the process. This period was less about individual galaxies growing smoothly and more about survival. Structures that could not retain gas faded. Structures that could adapt persisted. Over time, repeated mergers built larger systems. Gas cooling became more efficient as metals accumulated. Star formation gradually shifted away from explosive bursts toward more continuous processes. Only then did galaxies begin to resemble the systems we recognize today. This evolutionary path explains why galaxies have memory. Their present-day structure reflects not just how much mass they contain, but when and how they formed. Galaxies that assembled early carry signatures of violent beginnings. Those that formed later experienced quieter growth. Modern telescopes, especially those operating in the infrared, allow us to glimpse these early stages directly. Observations reveal compact, distorted systems at high redshift objects caught mid-assembly, shining in ways that betray their youth and instability. These are not failures of galaxy formation. They are galaxies in their most honest state. Understanding this era is essential because it marks the transition from a universe where light existed in isolation to one where light became organized into enduring structures. But it also raises an important question. If galaxies were so unstable, so violent, and so short-lived in their early forms, why did the universe need to pass through this phase at all? Why couldn't galaxies simply form later once conditions were calmer? The answer lies in the role darkness played earlier. The long night before the first stars was not wasted time, it was preparation, and the chaotic galaxies that followed were the inevitable consequence of that preparation meeting light. To see why we need to confront a counterintuitive idea that the universe stayed dark for so long, not in spite of progress, but because darkness itself was required for progress to occur. It is tempting to think of the cosmic dark ages as wasted time. Hundreds of millions of years with no stars, no galaxies, no visible structure can feel like an unnecessary delay. From a human perspective, it seems as though the universe could have moved faster, ignited earlier, and reached complexity sooner, but that intuition is wrong. The long darkness was not a detour. It was a requirement. If the first stars had formed too early, they would have formed in a universe that was not ready to support them. Gas would have been too hot, too diffuse, and too strongly coupled to radiation. Any collapse would have been unstable. Light would have flickered briefly, then faded, leaving little lasting impact. Darkness gave gravity time to work quietly. During the Dark Ages, matter was able to respond to the smallest imperfections left by the Big Bang. Density contrasts grew slowly without interference from intense radiation fields. Dark matter hallus deepened. Gas settled into gravitational wells without being immediately reheated or expelled. This period allowed structure to mature invisibly. By the time the first stars ignited, they did so in environments that could sustain their influence. Their radiation did not simply escape into an unstructured cosmos. It interacted with gas already organized by gravity, already on the verge of collapse. Darkness also ensured selectivity. Only the most massive and well-prepared regions formed stars early. This prevented star formation from occurring everywhere at once. Instead of a chaotic flash of short-lived light, the universe developed a staggered ignition pattern with stars appearing first in the most robust locations. That staggered beginning mattered. It allowed feedback to operate. Radiation and supernovae reshaped some regions while leaving others untouched. Chemical enrichment progressed unevenly. Complexity emerged in layers rather than all at once. In effect, darkness acted as a filter. It separated regions that could support long-term structure from those that could not. It ensured that when light returned, it did so in a way that could be sustained, amplified, and eventually organized into galaxies. Without this prolonged preparation, the universe might have remained bright but shallow, full of radiation but poor in structure, active but incapable of building anything durable. The long night was the price of stability. Only after gravity had quietly assembled the scaffolding of the cosmos could light return in a meaningful way. Only then could stars do more than shine briefly before vanishing. Darkness was not the absence of progress. It was progress without spectacle. And once that progress had reached a critical threshold, light was no longer fragile. It could propagate, multiply, and permanently alter the universe. This realization reframes the entire early history of the cosmos. The universe did not stumble into complexity. It prepared for it. And that preparation happened in silence long before the first star ever turned on. To see how all of these invisible processes fit together, we need to step back one final time beyond individual events and look at the early universe as a system learning slowly how to support structure. That broader view brings us to the final stages of the long night. By the time the first stars ignited and reionization began to spread, the universe had already done most of its hardest work. Not visibly, not dramatically, but fundamentally. For hundreds of millions of years, the cosmos existed in a state where nothing familiar could yet persist. No long-lived stars, no stable galaxies, no planets, and yet beneath that apparent emptiness, the universe was assembling the conditions that would make all of those things inevitable. This was the universe before it understood structure. Gravity was the dominant force, but it acted without guidance from chemistry or radiation. Dark matter shaped the large-scale framework, pulling matter into filaments and nodes. Ordinary gas followed, drifting into these invisible wells, heating, cooling imperfectly, and slowly responding to its environment. Nothing here was optimized. Cooling was inefficient. Collapse was slow. Fragmentation was rare. But that inefficiency mattered. If gas had cooled too easily, it would have fragmented everywhere, forming many small stars. Too early, flooding the universe with radiation before structure could stabilize. If collapse had been too fast, feedback would have torn systems apart before they matured. Instead, the universe progressed cautiously. The Dark Ages allowed gravity to separate signal from noise. Small fluctuations grew, large ones dominated. The cosmic web emerged not as something designed, but as something selected by physical law. By the time light returned, it did so into a universe that was no longer uniform. It entered a landscape already divided into dense nodes and empty voids, into places where stars could thrive and places where they could not. This is why structure feels hierarchical. Stars form inside galaxies. Galaxies form inside halos. Halos trace filaments shaped by dark matter. None of this hierarchy was imposed from above. It emerged from the long interaction between expansion, gravity, and time during an era when nothing was visible enough to betray what was happening. In this sense, the Dark Ages were not simply a waiting period. They were a phase of organization without illumination. The universe learned how to arrange itself before it learned how to shine. And once that arrangement existed, everything that followed built upon it. The first stars did not create structure from nothing. They revealed structure that was already there. Reionization did not organize the universe. It modified an organization that gravity had patiently established. This perspective changes how we interpret cosmic beginnings. The earliest visible objects are not the beginning of complexity. They are the first evidence that complexity had already taken root. Light was the announcement, not the origin, which means that when we look back toward the first galaxies, we are not witnessing creation in real time. We are seeing the moment when hidden processes finally crossed a threshold and became observable. And that brings us to the final insight of this story. If the universe required such a long, silent preparation before it could sustain light and structure, then everything that exists today, including us, is the outcome of that patience. We are not children of a sudden flash. We are children of a long night. Every star you see in the night sky carries the memory of darkness. Not the absence of light, but the presence of time. Time spent cooling, organizing, and preparing. Time during which nothing visible happened, yet everything necessary was set in motion. The universe did not rush to become luminous. After the Big Bang, it allowed itself to fade. Not because it failed, but because the physics of structure demanded restraint. Gravity needed time to amplify tiny imperfections. Dark matter needed time to assemble the scaffolding of galaxies. Gas needed time to gather cool imperfectly and approach the threshold of collapse. Only after this long preparation could light return in a way that lasted. The first stars did not end the darkness instantly. They pierced it, then multiplied, then reshaped the universe through radiation chemistry and gravity. Reionization followed, transforming the state of matter on cosmic scales. Galaxies assembled from unstable beginnings into enduring systems. All of that unfolded because the universe had first endured its long night. From our vantage point, it is easy to focus on moments of ignition. The first star, the first galaxy, the first planet. But those moments are only meaningful because of what preceded them. Darkness was not a pause in the story. It was the foundation of it. Every planet capable of supporting chemistry owes its existence to that era. Every stable galaxy owes its structure to the patient work of gravity during those early centuries of cosmic time, and every observer owes their ability to look back to a universe that did not hurry its own evolution. We often imagine progress as acceleration, faster formation, earlier complexity, quicker emergence, but the universe teaches a different lesson. Some things require delay. If light had come too soon, it would not have lasted. If stars had formed too early, they would not have built anything durable. If galaxies had assembled without preparation, they would have torn themselves apart. The long night made endurance possible. When we study the early universe today, we're not just reconstructing events. We are uncovering a pattern. Complexity emerges not from immediacy, but from balance. Not from speed, but from stability. We are here because the universe waited. Because it allowed darkness to do its work before allowing light to return. And when we look back toward that era, the silent stretch between creation and illumination, we are not looking at emptiness. We are looking at the conditions that made everything else possible. The universe did not become visible by accident. It became visible because it learned slowly and without intention how to support what would last. We are the evidence that it succeeded. The cosmic dark ages are not inferred from imagination, they are reconstructed from evidence. Even though this era produced no light of its own, it left traces, subtle signals embedded in the universe itself. Modern cosmology does not rely on a single observation to understand this period. It relies on convergence. The cosmic microwave background preserves a record of the universe just before darkness fell. Its tiny temperature variations encode the density fluctuations that later grew into structure. Measurements of these patterns tell us how smooth the universe was, how slowly matter could collapse, and how long star formation had to wait. Quasar spectra provide another clue. When light from distant quasars passes through intergalactic hydrogen, it carries absorption signatures that reveal whether that gas is neutral or ionized. The The gradual disappearance of neutral hydrogen absorption marks the end of the Dark Ages and the progress of reionization. Then there are galaxies themselves. Their distribution, mass and chemical composition all retain memory of when and how they formed. The smallest galaxies especially act like fossils. Their stars preserve records of early conditions revealing when enrichment began and how uneven it was. More recently, instruments like the James Webb Space Telescope have added a new dimension. By observing extremely distant galaxies, objects whose light left them during or just after the Dark Ages, we can directly test our models. We can see how compact these systems were, how chaotic, how different from galaxies today. Each observation alone is incomplete. Together they agree. They point to a universe that did not ignite immediately, a universe that waited, a universe that passed through a long necessary darkness. This is how cosmology works at its best, not by witnessing events directly, but by reconstructing them from overlapping lines of evidence that converge on the same conclusion. The long night was not hypothetical, it was real, and it shaped everything that followed. Which raises one final question. If darkness was so essential to the universe's early evolution, what does that tell us about where we stand now at a time when the universe is bright, structured, and aging? To answer that, we have to shift perspective one last time. We live in a universe that is no longer young. Stars have formed for billions of years. Galaxies have settled into stable structures. Heavy elements are common. Planets are widespread. The cosmic environment is calmer than it has ever been, and that calm can make the past difficult to imagine. It is easy to forget that everything familiar required conditions radically different from those we see today. That complexity was not immediate. That visibility was earned slowly. When we look back toward the Dark Ages, we're not just studying a remote chapter of cosmic history. We are examining a contrast, a universe that could not yet shine. A universe that could not yet build. A universe still learning how to support structure. That contrast gives context to our own era. We exist at a time when the universe has already done its hardest work. Gravity has organized matter, chemistry has diversified, star formation has slowed into a steady rhythm. Catastrophic events still occur, but they are no longer the dominant force shaping everything. In cosmic terms, we live in a mature universe. And that maturity is not accidental. It is the cumulative result of processes that unfolded during darkness, silence and delay. This perspective changes how we interpret discovery. When we detect the first galaxies, we are not seeing the beginning of order. When we observe the first stars, we're not witnessing creation from nothing. We are seeing the visible outcome of invisible preparation. The long night did not oppose light. It enabled it. And in that sense, the universe did not simply transition from dark to bright. It transitioned from unprepared to prepared, from simple to structured, from potential to persistence. We are not separate from that story. We are one of its late consequences. And the more clearly we understand the darkness that came before, the more precisely we can see what kind of universe we actually inhabit. Not a universe that rushed toward complexity, but one that allowed complexity to last.